Today we're going to talk about perturbation theory, and the first question is maybe why do we care? What is it? So what I would like to start with is maybe this idea you have heard of the variational method already in this lecture, and so you know that there is a way starting from molecules, starting from a system, to obtain its ground state energy and wave function systematically. Now the catch is, of course, that this is one way of doing it, but it sounds kind of silly to then do it over and over again for different systems. In particular, if they differ only by some extent. So the idea is that you use the information of something very similar that you have already and use that as a reference. Then you expand your properties or your energy or your wave function in corresponding steps. So what you then often get in terms of accuracy, we will go to that in a little bit more detail. That was an energy scale. And then what you would get is maybe something like this, where this is the reference. And then this is the first order. And this would be the accuracy at second order, and then the third order, and so on. So the hope is that you get close to some reference configuration, which is close enough such that you can then say, all right, this is sufficient. This is not perfect, but good enough. And in spirit, you already use that when you do the self-consistent calculations from earlier procedures, where again you say at some point this is good enough and you don't continue with a systematic improvement anymore. So in the variational principle, you would do one reference calculation and you would do that self-consistently, and then you would do that the same thing for the target, which might be something very similar and just somewhat close. I will give examples for that in just a second. But the idea is you have a solution, let's use it. And you may know that from other fields, this procedure, trying to trace out something that you already have. And the idea is you parameterize the path and then you connect two things, two configurations. Say this can be two molecules, this can be two configurations of the same molecule, or this can be something like a molecule in an external electric field. So if you think of it as some two configurations that you can connect, and you have two dimensions that describe that describe the individual configurations, then this can be anything. This can be a spatial dimensions, this can be an electric field dimension, so any of those. And you have two systems that you're interested in. There's one, which is the reference, for which you already have not only the Hamiltonian, but you may also have the wave function. And we will make use of this later on. Sorry. Now, we have another one, which is a target. And for simplicity, we will connect them. We will force any such path, or we'll define some path that gets us from one to the other. And this will be a one-dimensional path. So it reduces complexity. And this path will be denoted with lambda. So the idea is at lambda equals 0, you are at the reference, and for the target, you assume lambda equals 1. And this allows you to go smoothly from reference to target in this expansion. Now, you may know this from thermodynamics, where you do exactly this, for example, thermodynamic integration, where you connect these configurations, or you may know this from classical mechanics, where each of those points is one configuration, and now you have to do work in order to get from one to the other as a path integral. And there's a key aspect to this, namely that any point of this configuration needs to be state. So it needs to be a state function. That is most important because this means that we can pick any path we like, can look arbitrarily complex, as long as they begin and end at the same points. We will, of course, choose some path that is convenient to evaluate for practical purposes, but the main requirement here is that this difference that we integrate over to getting from reference to target shall not depend on the path. This is called the state function. So if you have state function, then this means that the difference of this is not a function of the actual path lambda that we choose. Maybe like this, like so. It's rather a function of only the reference of the target and the target. Let me check. Now, one of the common tricks now is you pick any of those paths you like, and now you integrate along that path. And then you say, imagine the state function would be my energy, because that's what we're mostly after. So then you can say, I have the difference in energy is the integral from lambda is 0, so from the reference, to lambda is 1, that's the target, over lambda of some function of lambda. Now, in the context of the energy, this function rather is the derivative of the energy. So that would be dE d lambda. So this means this way you integrate from 0 to 1, and at some point you end up at, you have recovered the whole energy difference. And that, of course, then is, if you do the integration, then you see that this is lambda of 1 minus energy of lambda 0. Just because this expression here is exactly the derivative. So you're integrating the derivative, which is evaluating the function itself at the boundaries. Now, you can also take these expressions and you can say, what if I do this as a Taylor expansion? And we will use that in the later stage of today's and tomorrow's lecture by saying that this would be the same as evaluating a Taylor polynomial. So I would be saying the energy of lambda equals 1, so the one of the target is the energy of the reference for lambda equals 0, plus this integral of the partial derivative of E with respect to lambda. And this can be expressed as the Taylor expansion going from order k is 1 to infinity of 1 over k factorial times the kth derivative of the energy. Now, this is not strictly proven. I mean, it's for all practical purposes, you can do that. It has some assumptions, some requirements to it, and we will talk about them in just a bit. So maybe for those more visually inclined, is this the idea is you have the two configurations, 0 and 1, and now you can have the derivative, the partial derivative of the energy with respect to lambda. That might look like this. And now what we do is we integrate exactly this part, and this gives us our delta in energy. So the idea is that all of these derivatives that you see here, and that's crucial, so let me maybe pick a different color, are evaluated at lambda equals 0. That means that knowing something about the energy of the wave function or the energy derivatives at one point already formally should suffice in order to get the properties of the target. And conceptually, that's very strong, because this means you have one configuration, say one molecule in some electric field, and now the response of that molecule with the change in that electric field in principle is encoded if you know the energy derivatives in this direction. So only being at one position in chemical space already would tell you something about the related elements. And this is exactly the beauty of this perturbative approach, that may be the hope that these individual derivatives can be used, and that, of course, in practice, you don't need this infinite sum of terms anymore, but you can rather stop early, and that already the initial configurations carry some weight and already explain enough of what's going on in chemistry. Right, that's the main idea. I see nothing in the chat. So in this picture now, let's formally derive this. This was the hand-wavy drawing part, but I would like to go about this with a little bit more formal rigor. So conceptually, you may know this quote from Archimedes, give me a place to stand and I will move the world. That's very close in spirit, even though he meant the mechanical lever. But here the point is, if you know something very well, this reference system and the reference molecule or the reference compound, and you know its response, which arguably is also a property just of that compound. If you know its response, then you can use that in order to describe its local vicinity. So what we do have of the reference, we know the eigenfunctions, which I will write like this, and we know its eigen values that would be the corresponding energies. And I will write the superscript 0 in order to make sure that this is the 0th order perturbation. So this is the properties of that reference system alone. But we also know something more. We know the full description of the system, because we know the corresponding Hamiltonian, the Hamilton operator, H naught. So this is something we know, and this is the unperturbed system. And now what we want is we want to react to a change in system, like a change in external interaction. Think of it as some minute disturbance. For example, imagine you have one molecule, and now you move another molecule closer to that one. If you only consider the electronic state of this one molecule that already exists, then initially, when the molecules are very far away, it will not notice the presence of the others. But now as it comes closer, now it feels the presence of the others, and the electron density rules will respond, and correspondingly, the energy will respond. Another example would be you have your molecule, and now you turn on an electric field, or you turn on a magnetic field. So in principle, that's all the same thing. Or imagine you have an angle, and now you rotate this angle of the molecule, some degree of freedom. You rotate it about. That's again a small perturbation in the sense that almost everything of this molecule is the same, like the dominating configurations. It's part of its system description that changes. Now, of course, you can just sit down and say, all right, I rotate the molecule a little bit, I create the new Hamiltonian where the external potential formed by the nuclei is slightly different. And then I just solve it. Now, in principle, there is this direct correspondence between the Hamiltonian and the solution, but we would like to make sure that it's only, or make use of the fact that it's almost the same as what we had before. So what we say is there is a change in system. That could be geometry, that could be magnetic field. So the idea is you define one Hamiltonian and you say, now I take the one of my reference system, which is essentially unchanged, and now I extend this plus some perturbation. And what you have here in the superscript, that is not the derivative. This doesn't stand for the derivative. It's the corresponding change in the Hamiltonian. So it's of the difference between the Hamiltonian of reference and target. It's the difference that you can explain just by linear response. And this is the strength or magnitude of the perturbation. Now, this way you have a clear separation. You know that the one of the Hamiltonian of both together, so the one approximating the Hamiltonian of the target system, is the reference plus some minute change. As one idea, or as one example, if you take the 1D harmonic oscillator, then you can get the Hamiltonian of the plain simple reference, and that's the kinetic term, which gets added to the potential term, and this is this harmonic oscillator, so that would be k half x squared. Now, the perturbation to that could be what happens if your harmonic oscillator is not perfectly harmonic, as, for example, chemical bonds are not. And what happens if there are some higher order terms that play a role? And then you could say, what if my new Hamiltonian is this reference part plus some linear change that I add? And that could be, for example, in this case, the same expression as what we had before, k half x squared plus lambda of h1, that could be, say, adding a cubic and a quartic term. And this then would go towards an unharmonic oscillator. We will come back to this particular expression later on. So perturbation theory effectively is just one simple idea, namely do a Taylor expansion of the Hamiltonian of the wave function and then corresponding also the energies. Now, there is no strict need for this perturbation to be small. There's no formal requirement for this, but if it is small, if it's only a minute change, so if the perturbation is small, then only the leading orders should suffice. Because otherwise you can argue that, well, rather than solving for these, in principle, millions of infinite contributions here and this infinite sum, I'd rather have something where I only need to do the first few leading orders, because otherwise I could just directly do the true target function to evaluate that on its own. Now, there's one restriction in that regard, And this one restriction is that, at least in today's lecture, we will not consider degenerate configurations. So if you have two things, say two molecular orbitals, where on your energy axis you would have, say, the benzene case. So, about on my drawing as physicist, where you have this kind of orbital at the same level as this kind of orbital, then without the perturbation, they are degenerate, but under applying the external field, this degeneracy is lifted. So here we will not consider degeneracy. That's the treatment of that is then part of advanced quantum mechanics. So here the behavior of the two would be different depending on the field, even though at the reference they have the same energy. Now, this also means that we can assume that the different energy levels are distinct. So N and M, different levels must have different energies. Now, let's do the formal Taylor expansion. So let's say we have our Hamiltonian, the Hamiltonian of the target, and this one, so without lambda as index, this one is the Hamiltonian of the reference. I will write the first terms explicitly. So this is times lambda of the first perturbation and then lambda squared of the second order perturbation. And the idea is here that you consider lambda as a measure of magnitude and change. So if lambda is very small, because you're only doing small changes, then lambda squared, again, is much smaller. So we will use the fact later on that this perturbation should become smaller the higher the order in lambda is, because then this effect gets suppressed by the continuous multiplication. Now there is a different way how to write that in the picture of the Taylor expansion, where you say you have this reference Hamiltonian plus lambda times the derivative or partial derivative with respect to lambda of this Hamiltonian, which is a function of lambda, evaluated at lambda equals 0. So that was what we had before, this point that you only need the information at lambda equals 0. And then in the Taylor expansion picture, you would also get then the lambda squared expression, but there's a prefactor of 1/2 in there, which will come from, so this squared is the lambda squared in the Hamiltonian of lambda at lambda equals 0, and then higher order terms. And now the coefficient comparison tells you that this term and this term need to be identical, and that this term and this term are identical. Now, we can do the same thing, what we did here with the Hamiltonian. We can do the same thing with the wave function and the energy. Since this is a coefficient comparison, meaning that any change that we do should be reflected up to that order, these terms can then later on be combined. So how does it look like for the wave function or for the energies? And for here, if we say our wave function psi j looks the same thing, looks the same way. So again, we have our psi j 0, the one of the unperturbed reference system, plus the change of the wave function because of this external perturbation, because of some change in the system. So the idea is that the first term already covers almost everything, and then the second term only some higher contribution. Then we have lambda squared. And again, we get the same part plus some higher order terms. So correspondingly, you can look at the Taylor expansion picture. And in the Taylor expansion picture, you can do the same expansion. And what you will then get is the wave function psi j, its derivative at lambda equals 0, lambda squared. It's exactly the same expression now that you get psi j this time. Those individual terms. So I'll not write this down explicitly for the energy, but you will get the idea. In all of those cases, again, it's the important thing is to identify the corresponding orders in lambda, and we will use this regularly in considering the different expressions. Nothing in the chat. Okay, so this is as above. Wave exchange psi full. Now, more compactly, this can be written as a series expression. So then you say this is the Hamiltonian of my target system is the sum of k is 0 to infinity. So it's 1 actually. No, it's 0 because we need the 0th order derivative. So, and this is then 1 over k factorial of the kth order derivative, which I will now write as this. So it's shorthand, it's a shorthand notation. That would be for d k d lambda k. And then this is the Hamilton operator as a function of lambda, but evaluated at lambda equals 0. And the important thing is that this part here, this evaluated at 0, actually applies to the whole thing, right? So it's the derivative, it's the derivative evaluated at that point, not only the Hamiltonian. Now we need, in the Taylor expansion, we still need lambda to the k as prepared. So this you can do for the Hamilton operator, and you can also do the same thing for the corresponding wave function for the eigenvalues, eigenvectors, and then later on the eigenvalues. The concept is the same. Again, you get this infinite sum expression. Just because it's so important, let me write them out here individually such that it becomes clear. So that would be the kth order derivative of psi j evaluated at lambda equals 0 times lambda to the kth order. And correspondingly, you have the eigenvalues, which are done the same. So 1 over k factorial j at lambda equals 0 times lambda to the k. Now, here, these things, they, in principles, under some assumptions, are sufficiently rigorous and smooth. So, in a sense that they can actually be Taylor expanded. Now, you can't do the Taylor expansion on each and any function. It's not universally guaranteed that you can do it. And the way this is done is we need a few assumptions, and they are important to clarify. So this is something to keep in mind, but it requires assumptions. And the one assumption that we have is that all these functions are sufficiently differentiable, because otherwise you can't get these individual these individual derivatives. So to get the 100th order of some function, it needs to be differentiable. So that would be infinite list. The second thing is, because you not only because you have these, you need these derivatives explicitly, you also need that that actually converges to something, and that it also converges to the true value. That's not universally guaranteed. So, but it's for many cases, there's numerical evidence highlighting that this can be done even, and this actually converges even for really crazy changes where you change the elemental composition of a molecule. So this expansion should converge, and these are mathematical assumptions, but there's also a practical assumption, and this practical assumption is that already the first orders are helpful. Most importantly, there's no strict requirement that this perturbation is small. So that's not a requirement. From a practical perspective, it does make sense because a small perturbation increases the likelihood that the first few orders are already explaining it. But in this formal derivation, there's no requirement whatsoever that this perturbation actually needs to be small. Now, if you look at this expression that we had before, for example, for the wave function, there's one technicality that needs to be sorted out. And this one technicality is the fact that we need normalization along the way. So we need to make sure that these terms, that the original wave function, the original one that we had, the eigenfunctions, which are normalized, stay as such as we continue. So under the perturbation. So let's have a look at the normalization. So what we start with is the requirement that for the solution that we already have, we know that the individual eigenfunctions are orthonormal, such that psi n0 and psi n0 is 1, or more generally, that psi I0, psi J0 is Harmonic delta ij, so that means 0, 1, 0, 0 if I not equal j, 1. We will use this Kronecker delta for shorthand notation. Now, this is something we already know, which is guaranteed from earlier cases. Now we will say that our psi n, so the result of this Taylor expansion here after that infinite order shall be orthonormalized again. So we say that psi n0 again. This can be enforced by by just defining some prefactor, which would be then this for normalization. So there's no special insight in why that is. We can always make it as such. Now, the question is what's the relationship between between these individual terms. We can, this psi n is an expansion in perturbed eigenfunctions. So it does change as we, it does include more contributions as we add higher orders. So let's have a look at what this means for the individual expressions. So this one here can be expanded. So this 0. The right part of this is this infinite sum. So I can take the ket here and can say, so this is 1 as we enforced before. So now we say this would be psi n0, psi n0, because that's the leading order term, plus lambda of psi n0, that's the left side, so the bra always stays as is, but the ket now increases in expansion order, plus lambda squared of psi n0, psi n2, plus higher order terms. And you see that the one part here is in lambda, the other one is in lambda squared. This one we know from earlier parts is 1. So the residual terms, the infinite order terms need to be 0. And this we will prove formally after the break. So now there is a 15-minute break and we continue. Let's have a look at, in particular, these two last terms that we have left over. So these ones, the question is, what are they actually in terms of my volume? And we can show that again by looking at this the Taylor expansion perspective. So we start from the requirement that our individual, the Taylor expanded functions should be normalized to 1. And now let's look at the first order only. So if that is true, then to first order. If that is true, then we first have these two cases plus lambda first order. So that's for this left bar psi n, that is the Taylor expanding into first order. And then this is times the corresponding kets. And that again is these kets. Now we can multiply those out. Then what we get is psi n index 0 plus lambda psi n1 psi n0, that's now terms 2 and 3, plus lambda psi n0 psi n1 plus lambda squared expression on psi n1 psi n1. Now, as I mentioned before, when we consider something to be expanded up to first order or to nth order, this means that anything which is in the higher order of lambda is treated as if it were 0, which means that this term over here is 0 in first order. That leaves us with 3 terms, for the first of which, pardon, for the first of which we already know is 1. We know this because this is one of our reference solutions, and they have been obtained following their normalization procedure. So this we know is 1. That leaves us with 2 other terms. So this means we can subtract this one from the one that we had before, so 0 is lambda psi n1 psi n naught plus psi n naught psi n1. And now, without loss of generality, we can assume that these overlaps or these integrals are real. If they are, then you can change the order of these of brackets, and this means we get 2 lambda psi n0 psi n1. This means, of course, that this bracket needs to be 0. That means for our expansion, if you think about it, this bracket that we have over here, we find back in our expansion over there. So this means, maybe I can use, so this means it's 0. Consequently, you can do the same thing for this one, and then you find that this one is 0 as well. It's the same logic, same procedure. Now, in this case, you would do the expand up to second order, then use the fact that you already have shown that the other terms are 0. So with this, we now have a few expressions that we can make use of. We know what's the integral over psi n mod and psi n, and we also have the reference, and there's the final value, and we also have our normalization from the reference. Equipped with this, we are now ready to look at Schrodinger's equation. So in the concept, in the fundamental Schrodinger's equation that we have is that the Hamilton operator acting on the wave function is En times S. Now, for each of those, we have a Taylor expansion, remember? So for each of those, there was this part here, which in the box, we have this Taylor expansion, and now we can insert the leading orders of this Taylor expansion in this. Insert Taylor expansion. If we do that, then what we obtain is this part. The Hamilton operator was, as a Taylor series, was the Hamilton operator of the reference plus lambda times the linear perturbation to it plus lambda squared the quadratic perturbation to it plus higher order terms. I will not write all of them. For the wave function psi n, what we have was psi n of our unperturbed reference plus lambda times the linear response to that plus lambda squared of the quadratic response to that plus higher order terms. Now, this means this is equal to the same part with the energies. So that would be the energy of the reference plus lambda times the linear response of the energy plus lambda squared of the quadratic response plus higher order terms. There will be no surprise that the right bracket is exactly the same, so I will just copy it for completeness sake. That's again okay. Now the thing is, we will get individual perturbation equations, perturb equations, and this will allow us to actually solve this the system mathematically. Now let's collect these terms, because I would like to collect these terms in the individual order, meaning basically in the exponent of lambda, the power of lambda. And we would like to do that because in the individual expressions, the individual equations need to be satisfied for each such order. And that means that we get individual equations which are then easier to solve. So that's why we now we will dissolve those expressions and we will group terms in order of lambda. Now, for this to be a little bit clearer, I will subtract these two functions from each other. So that would be equivalent of saying that Hamiltonian times the wave function minus the energy times the wave function. So we will group terms and then write them following that convention. All right, so let's collect the zeroth order terms. So what about the everything which is not a function of lambda, or does not have lambda as prefix? So that would be exactly our H naught that we have, and these four terms. Those are the only ones that don't have lambda as a prefix. So if we write this down, then we get H Hamilton operator naught times the energy minus the energy times the wave function. That's our first term. Those are exactly all there are that are zeroth order of lambda. Now let's collect those which have lambda as a prefix. And now this is somewhat difficult because there are two such combinations how you can make this work. You either have something that is in zeroth order of lambda times something that is this one times that one, which is first order of lambda, or those are the individual cases that you collect. There's four of these terms. So if you do that, you gain Hamilton operator, the linear response minus the corresponding energy, but applied on the wave function of the reference, plus zeroth order term applied on the perturbed wave function, so the linear response wave function. And that's exactly because you need to collect precisely one lambda, so you need to mix terms which have 0 and 1 lambda correspondingly. Let's have a look at the squared expression. So lambda squared, and again we can collect those terms. Now we have to either combine something which is linear in lambda with something that is linear in lambda as well, or something that is quadratic in lambda with something that is zeroth order in lambda. So this is the reason why we now get three such groups of terms. So now we get the quadratic response, but on the reference wave function. So that would mean the lambda squared comes from whatever's in the brackets here, the parentheses, plus the case where both are linear in lambda. So that would be 1 minus plus those cases where the Hamiltonian and the corresponding energy are 0 order in lambda, and the wave function is quadratic in lambda. So let's maybe color code this so that this becomes clear. So here both are blue, and blue shall be 0 in lambda. This is linear in lambda. Then this shall be quadratic lambda. And then, so here you have, this is a combination of something which is quadratic and something which is 0th order in lambda, or for the other term, for the first term, it's the other way around. And you can have the case where something which is linear lambda times linear. So the orders in lambda always need to be combined to 2. And the middle one, we have this kind of configuration where there's always one term which is 0th order at lambda and 1 is later. So basically you collect these terms as you get them from multiplying this infinite series. This is somewhat hand-wavy because you can't just multiply infinite series, but for the leading order, since you can do that for every individual order, then it becomes a finite summation again. This is actually rigorous. However, what you do get is the expression for the 3rd order term, because this would still be possible in the summation that we've wrote, plus of course all other higher order terms. Now the trick here is to realize that because lambda can vary, lambda can have different values because we can tune this interaction. We can change the interaction to be of any strength, of any magnitude. This means that this expression needs to be satisfied for any value of lambda. And the only way to do that is if not only the sum of all those terms actually is 0, but also if each individual coefficient of lambda is 0. So maybe as written as an expression, we can here say that this is the function of individual coefficients, a polynomial in lambda and so on, which means that this is a regular polynomial and this needs to be 0 for all possible values. And the only way to satisfy this is if each of those need to be 0 independently. But now what does it mean practically? It's a nice thing to have, but what it means is that all these expressions that you get here, they can be separated into individual terms. So you get the first line as one equation, and the second line, so at least the part within the parentheses, that is another expression. It needs to be 0 independently. And this now allows us to recursively solve these for those perturbative terms. Now that's maybe again an important result to keep in mind. You get Schrodinger's equation gives you multiple perturbative equations. So in the 0th order, you get something that you already know, namely that 0 shall be the Hamiltonian of the reference minus the energy of the reference times the unperturbed wave function. This you know, that's a Schrodinger's equation that you already just solved for the reference system. But now you get expression for the individual changes. So you get in the 1st order, you get 0 is everything which we had in this bracket here, right? Everything in there. That's what we now get here, because that needs to be 0 individually. So that would be the linear response Hamiltonian minus the energy times the unperturbed wave function plus the Hamiltonian, the unperturbed Hamiltonian minus unperturbed energy times the reference and then the perturbed wave function. Now you see that effectively here we already get these contributions and we can insert them in the next expression, in the next order, and then use the next order expression to solve for eigenfunctions in psi n. So we continue this to the second order because we had it above. And in second order, we now take everything which comes from this second bracket over here, or the third bottom, third one where everything is quadratic in lambda. And that would mean that we now have the terms second order Hamiltonian minus second order energy times unperturbed unperturbed wave function plus the first order response in Hamiltonian and in energy times the first order response in wave function, and then finally only the reference case, so the zeroth order unperturbed Hamiltonian minus the unperturbed energy times the linear perturbed, the quadratically perturbed. Now here you see again that these wave functions can be used in the second order expression, but now we also got these terms here and we can use them in the next order. This way we build up this successive approach of solving these equations. So the key takeaway here is that you start from Schrodinger's equation, you Taylor expand each individual term, and then you collect the terms in orders of lambda. What you end up with are these independent, not strictly independent, but these independently solvable expressions for the individual order terms. And they can be used, they can be solved then consequently one by one. Let's have a look at the consequences of this, because there is some dimension to it to understand which information, so which perturbed wave function is required to get the energies at a given order. And there is something that is somewhat counterintuitive, but is conceptually very powerful. So let's derive this to see which kind of responses of the system do I need to know in order to get the energy of the system up to a certain order. And we will use exactly these expressions. So how to get these energies? So perturbed ones, right? Let's put like a J next there. Let's start with the first order expression. So that would mean we take this one. So we start from the expression, I just copy it over. So this would be the perturbed Hamiltonian energy times the unperturbed wave function plus the unperturbed wave function so the zeroth order times the first order perturbed wave function. Okay, so this is the same expression that we had before. So the question is, we would like to get this one here. So this one is what we want, because this one is what we have. So there's no surprise. Now, this would be nice because this tells us how does the energy change as you go to the next order. You maybe remember this plot that I showed in initially, where we had the energy, and now the next order then gets increasingly more accurate. And the question is, we have this one, and now what about this one? So what's the next? And how we do that is we take our individual wave functions, and we will project this onto some trial wave function. So idea, project onto psi m. Okay, now we can just write this down for all our terms, and I will put them on different sides of. I will bring one of those two terms on the other side of the equation. So this is just plain insertion. So you left multiply with this bra of that individual state, and then you get first the Hamiltonian. This is first order minus the energy, which you can pull out because it just is scalar values, so consequently it does not need to stay in the bracket. And that is now, that was the part here from the right, this one, and now let's add this on the other side. Again, we can bring the energy expression to the front. N 0th order times n 0th order minus the Hamilton operator, at this time in first order perturbation on psi n. Let's just take the first expression and then left multiply with this graph. Now, here we now know something about individual terms. For example, we know that this part over here, that needs to be the Kronecker delta Nm. If n and m are the same, then this is 1, and if n and m are different, then this needs to be 0. Now, we can now look at the first term of this alone, and we can rewrite this term a little bit. So let's pick this term here alone. And this term is the same as take the complex conjugate and moving or exchanging the order of bra kets and make this ket bra. So what we then get is psi m1, psi m0 complex conjugate. Now, here we can use the property of the Hamilton operator, and we can get the energy out of this. So that would be the m complex conjugate times psi m1 psi m0. Now, the energy function, the energy values are real. So this is the same as saying this is without the complex conjugate. This can be turned around again. So this would be psi m1. So we apply the complex conjugation once. So effectively, we found a way to left apply our Hamilton operator. This requires to go complex conjugate once and complex conjugate twice. Now we can take this expression here and then insert it for what we started with. So if we do that, then we take first, well, this part here. So that would be En0 psi M0 psi N1. And now the rest of the equation, we take whatever was written here, right? So this part we copy. So this would be minus En0 psi N psi N1. And then this is equal to N1 psi M0 psi N0. Actually, I can just shorten this because we already know it's the Kronecker delta, so that would be delta Mn minus the last term from above, so that would be unperturbed state M times the linear perturbation Hamiltonian times the unperturbed state N. Now here the first two terms can be grouped because this one is the same as this one. So we can say this is En0 minus En0 psi N1. And the right-hand side remains unchanged. Copy this for completeness sake. Okay. Now what we have is an energy expression that on the left side has the energy difference between two configurations of the unperturbed system. And on the right-hand side contains this energy that we actually care about, N1. So let's look at the case if N and M is the same. Because this energy expression over here only remains if N and M are the same. Because otherwise the Kronecker delta will drop to 0. So in the case of N is M, we know that the energy difference of En0 minus En0 needs to be exactly 0. It's the same energies. We also know that this delta NM becomes 1. So what we can do is we only get key terms on the right-hand side. So we can say that in this case, En1 is psi M0 H1 psi N0. Because this M over here becomes N. In that case, those will be the same. So that means we now have, that's quite interesting, we get the energy of the perturbed configuration, so the linear response energy of things, we get just from looking at something that we already know from the unperturbed system, namely the corresponding wave function, and something that is part of our problem description, namely how to change the Hamiltonian. I mean, we defined what this change is, for example, changing some electric field. So we know exactly what this is, meaning that the linear part of the energy response, the linear part of the energy perturbation, directly follows already from two things that we happen to know. Which is awesome, right? There was no change in, or no additional calculations necessary. We just combine things that we already know, and we end up at this energy. So that's also one important result to keep in mind. And we will refer to this as, we will define this as the linear part of the Hamiltonian HNN. So that's just one new label that we will attribute to this particular energy. Okay, now this was for the first order part, and it's quite an interesting result, because it means that you already get the energy derivative from this change in corresponding Hamiltonian alone, and this result is quite central. It has a separate name, and it would be easier to see that. Just write it a little bit differently. So I would say that the linear part in this change in energy, that is exactly the first order contribution of this one energy. But that is, as we just have shown, this is this expression. So the expectation value of this perturbation operators to first order with the unperturbed wave function. And this then is the, if you remember the identification of the individual terms that we had in the Taylor expansion, so where we started, then this part was, this H1 was the change of the Hamiltonian with respect to our interpolation parameter lambda. With this. Then where we started from, we said that we can identify, there was this big table that we had earlier. Let me go back to that. So here we said we identify, that's these points here, this one and this one. We said we identify the derivative with this linear term in the Hamiltonian, because they are the same order of magnitude. That means that here we can do the same, we can do the reverse substitution, and this expression over here, so this one and this one, that's the Hellman-Feynman theorem, or the electrostatic theorem if you look into old books. Hellman-Feynman theorem. That's quite convenient because it gives them a handle on changes of molecular properties with respect to some external changes. And imagine, for example, what is the force? The force acting on some molecule is the derivative of the energy with respect to spatial coordinates. So if you know the change in this perturbing Hamiltonian, in principle, you can get forces on molecules directly from only having the original wave function at hand. And that's a quite powerful result. In practice, there are some limitations to this, but this again, I would consider this to be a central part or a central thing to keep in mind from this lecture. Okay, now we have this harmonic oscillator earlier in the derivations, and I would like to circle back to that one and maybe give an example on how this would look like from an numerical point of view. So let's do one example. And we have this one-dimensional anharmonic, so 1D anharmonic oscillator. And we said that our perturbing Hamiltonian at 1 shall be defined as some cubic term and some quartic term. You might have thought, why add both of them at the same time? We'll just start with cubic. We will come to that in a second. Why that's too relevant. Now, we also know from this for this particular case, we also know the expression from just before, right? We know what is the perturbing energy because of this change in Hamiltonian. So we know that the linear energy part is the ground state wave function times this perturbing Hamiltonian times the ground state wave function again. So that's the expectation value of this particular perturbing operator. Now, we also know there's analytical expressions from the harmonic oscillator, because the harmonic oscillator is much easier to solve. So you can think of it as like one of those cases where you solve the harmonic oscillator, and then you change the result that you got because of the nice properties of the harmonic case, and you perturb them towards the anharmonic case, which otherwise would be harder to solve. And if you do this, so here we know that the wave function psi naught is alpha over pi 1/4 times e to the minus alpha x squared over 2, where alpha is defined as 2 omega n h bar. This is the solution that you get from the harmonic oscillator. Now we can plug this in, and we can say now our first order energy is exactly this expression that we have above. So maybe I just do it like this. So that would be first alpha over pi, square root now, not to the power of 1/4, because we get 2 of those. So there's 1 alpha from the bra and 1 from the ket. Now the integral becomes this, is dx e to the minus alpha x squared over 2, actually. Yes. No, not over 2, because we take the product of the 2. So we have 1 the bra, 1's the ket. So the over 2 gets lost because it cancels with the times 2. Now we have this perturbing Hamiltonian, so that would be cx cubed plus x power 4. That's exactly what this bracket does, right? It's the integral in space of the product of those 2 functions. And since this is a 1D case, it's only the one integral in x direction. So now we can take this term here, and we can say, now remember here's a cubic term and there's a quartic term. And now the thing is that the cubic term is an odd function, meaning that its symmetry is it changes sign if you change the sign x. So you can imagine this is even, and this would be an example for an odd function. So this means that since the first one, this exponential, is an even function, we have an integral over everything here, where we have some even function times some odd function. And that integral needs to be 0, which is the reason why there is no cubic contribution alone, which is why we need the quartic one. So then what we get is alpha over pi from minus infinity to infinity, x e to the minus alpha x squared x4, where d is a parameter here, not the integral. And this has a standard solution. In this particular case, you can simplify this and say this is alpha over pi integral from 0 to infinity. Now it's twice that, so dx times 2 e to the minus alpha x squared x to the 4 and d. And this you can look up as a standard solution, 3d alpha squared. So we didn't have to solve the total case again for our unharmonic oscillator when we add some perturbation, but we could rather reuse the information that we had before. We could reuse the individual wave function, and this way get a first order approximation of the unharmonic oscillator. With that, I would like to close for today, and thank you very much for your attention. And we will, if there's any questions, please let me know, but I didn't see anything in the chat. Otherwise, we'll continue this tomorrow. Thank you very much.